Good morning, everyone. I'm Lei Chen-Hu, a postdoc in Dr. Hachin's group at the University at Buffalo. And the title of my talk today is Carbonized pyrophosphoric acid doped PBIs for high temperature hydrogen CO2 separation. And my talk contains three parts. The first is introduction of membranes for pre-combustion CO2 capture. And second is our approach of membranes for hydrogen temperatures hydrogen CO2 separation, which contain two steps. The first step is using pyrophosphoric acid or PPA to close in polybenzimidate or PBI, and then we carbonize those closed-in PBIs to produce carbon molecular size membranes or CMS membrane, and final conclusion. As we know, there are three main ways to capture CO2 from coal-fired power plants. One is pre-combustion CO2 capture where fossil fuels was gas-fired to produce hydrogen and CO2. And as all we know, gas transport through membranes based on solution diffusion model. And gas permeability it depends on gas diffusivity and gas solubility, and gas selectivity depends on diffusivity, selectivity, and solubility selectivity. As hydrogen has a smaller molecular size while CO2 has better condensability, hydrogen CO2 solubility selectivity is always below 1, while hydrogen CO2 diffusivity selectivity is above 1. So if we want to get high hydrogen CO2 selectivity, we should enhance the receiving ability to achieve high diffusivity selectivity. So why we choose PPI? Firstly, PPI contains lots of intermolecular hydrogen bonding, and this causes tight packing of PBI structure and provide it strong size-saving ability. Compared to other glassy polymers like PIMs, polyimides, or CA, PPI has higher hydrogen CO2 selectivity above 10. Another thing, as PBI structure is really rigid, and its glass transition temperature of PBI is above 400 degrees C, which means gas separation can operate at high temperature, and we really benefit from high temperature gas separation. For example, hydrogen permeability of PBI can increase from 235 degrees C to 30 and 150 degrees C with no decrease on hydrogen CO2 selectivity. But if the hydrogen permeability or hydrogen CO2 selectivity is too low to use in particle application. So we once try use use phosphoric acid to closing PBI, and we get high hydrogen CO2 selectivity above 100. But there is a trade-off between hydrogen permeability and hydrogen CO2 selectivity. We once carbonized pure PBI, and we get some good performance and high carbonization temperature. But high carbonization temperature always means bad mechanical stability. So here our approach. First, we use pyrophosphoric to closing a PBI with hydrogen bonding and prompt transfer. As pyrophosphorate has more acid groups and can generate more hydrogen ion, this closing can be better than PBI phosphoric acid group. And then we carbonize those close to PBI to create more free volume for gas transport and low carbonization temperature, say 600 degrees C. So firstly, we use doping level to represent costing decrease of PPI, PPA, and we get varied doping level by changing the acid PPI molar ratio in the acid doping solution. And from the XLD patterns of those acid doped PPIs, we found that there's no peaks for crystal PPA. That means all PPA was all PPA was dissolved in PPI, and also we find both the peak of PPI moved right, and that means the spacing decrease, and this enhanced our size saving ability. We also test densities of our acid double PBIs by buoyancy method, and then we use additive model to analyze those densities. And finally, we calculate the PPA density in PPI is about is 2.25, which is little lower than that of pure PPA or crystal PPA. And this result shows that crystal in PPA fully dissolved in PPI and become amorphous phase. Then we test pure gas hydrogen CO2 separation performance at 150 degrees C. So firstly, for hydrogen, this permeability have little change before the high doping level at 2.42. For CO2, its permeability decreased with the doping level, and this causes hydrogen CO2 selectivity increase first and then decrease, and the doping level of 0.34 obtained at the acid PPI molecule of 0.5, we get the best hydrogen CO2 separation performance, and then we use this doping condition to produce membranes for CMS membrane. So first we carbonize, so we sandwich those acid WPIs in ceramic place and go on the carbonization procedures. I mean, basically, uh, there's, I mean, in tradition, people use complicated and tedious heating protocol, which is also time consuming. Here we want similar heating protocol like that. We just hit rapid the temperature from room temp to 600 degrees C directly. And to prove this simplified proton, it's work for us. First, we check the weight loss by the thermal gravity, and we find that compared to traditional proto, the weight loss by simplified proto it's a little lower than traditional proto, and also we test the hydrogen CO2 separation performance, and we find at 600 degrees C after 600 degrees after carbonization and 600 degrees C, we can get a similar performance with, from traditional proto and simplified proto. And then we use a simplified proto to carbonize our costing PPA or PPI, PPA. And first, we find the weight loss of pure PBI between pure PBI and PBI PPA are similar, and this proves that acid was still is the acid stays still stayed in the film. And then we test scatter density and also bulk density of those of PBI CMS and PBI PPA CMS, and we find that compared to the PBI CMS, PBI PPA CMS show lower porosity. And then we also test pure gas hydrogen CO2 separation performance of all CMS and 150 degrees C. So firstly, for both PBI and PBI PPA, after hydrogen permeability increase, gas permeability increase after carbonization. Well, but with the loss of hydrogen CO2 selectivity. Uh, and compare pure PBI CMS. PBI CMS show little lower hydrogen permeability but high hydrogen CO2 selectivity. Then we compare those performance with upper bound, and we found that so firstly, for acid doping, we can increase the hydrogen CO2 selectivity with a little loss of our hydrogen permeability, and then we carbonized the best costing PBI and get high hydrogen permeability and 200 partner with with half loss with some loss on hydrogen CO2 selectivity. So we can draw conclusions here first. PPI can be closely use PPA, and the closing can increase hydrogen CO2 selectivity with little change on hydrogen permeability. Two, PPA can stay in PPI during the carbonization at 600 degrees C and cause a low possibility of the CMS membrane. And third, after carbonization at 600 degrees C, both PPI and PPA show improved hydrogen permeability but decreased hydrogen CO2 selectivity. And here I need thanks my advisor, Dr. Hatchin, who gives me a lot of support and suggestion. And I also need Ring and Skinny for gathering data. And also I need to thank all my groups, all members in my group, and also we need I need to thank the funding from DOE project. So that is my talk, and I'm glad to answer your question.